Hello everyone, welcome back to my AI mini-series. Today we are asking the question, what is a transformer anyways? Looking at the T in GPT, in general looking at the history of AI, how did we get here, and maybe even where are we going. So this is a part of a series I'm working on, so if you want to click here for the full playlist, otherwise you can just watch these individually as well. I also have a playlist that I put together of videos I watched as I was researching this. So if you want to watch that, you can as well. We're currently in a AI arms race. AI research, it feels like it's moving at a lightning pace, but we're not really moving that quick. The majority of videos I watched in the playlist were over 5 years old. The transformer model itself, the T in GPT, was invented in 2017. And the big innovation that's changing the world right now, ChatGPT, is just taking this existing thing and making it bigger and more expensive. So we'll talk about that point when we get there. But for now, let's go back to the very beginning. What is artificial intelligence? AI is as old as computers themselves. AI is a fairly fuzzy term that we apply to systems that are supposed to exhibit some kind of intelligence. So an example, Microsoft Windows XP, let's say. Very complicated computer program, operating system, all sorts of stuff in it, not considered an AI. 5-line script that moves a paddle up and down in a game of Pong, that is an AI. Feels arbitrary? Yeah, kind of is. So the word AI, at least originally, applied to problems, not to solutions. So early AIs were following a script that humans wrote. There's no functional difference between AI code and code. There were some fun concepts like tree search or min-maxing or whatever, but these concepts could be applied to any problem, not just applications that were marked as intelligent. The next stage of AI, though, was to start copying the human brain, or at least a single cell of it. These cells were called perceptrons. We mostly just refer to them as neural networks nowadays. This part may sound scary or even magical, but it's important to keep in mind all we really made here is a fancy math equation. Perceptrons are an idea, but it's just math when you look into it. So making brains fun and all, you can string together a bunch of these equations or perceptrons into a larger network, but it's pretty useless if you can't teach it to think somehow. Our solution to this problem was more math, specifically a special function called backpropagation through gradient descent. This is one of those things that defines all modern AI systems. As an analogy, consider some other complex design space like quantum computing. You can't just do anything with a quantum computer. You need to express your problem in terms of an infinite series that can undergo waveform collapse to reveal the answer. That also sounds complicated, but the point is, not every problem can be solved with quantum computing. In fact, we already found a way to store passwords that are quantum safe. Same way, not every problem may be solvable by AI. If we want to understand what modern AI systems are capable of, we need to first understand this complicated math thing, gradient descent. It's quite technical, but here's my best explanation I found. Water flows downhill. Okay, there's some calculus if you want to simulate water flowing down a complex problem space. It's just the derivative, by the way. But that's really all there is to it. The whole idea of gradient descent is just finding a way to express your problem in terms of where's the minimum. And if you can do that, you can solve your problem. So let's take a look at real AI problem space. Say I want to create a computer system that can receive handwritten digits as an input and output the number that is in the photo. So instead of asking the question, what pictures relate to what answers, what if we ask the question, what numbers will minimize the number of mistakes when mapping these photos to these correct labels? It feels like a hack, but water flowing downhill can actually solve this complex problem. So we have a system that can solve a math equation that can in turn solve an arbitrarily complex problem. Let's try teaching it to talk. And there's another problem. So let me illustrate that one. Suppose you have a word in a sentence and you want to know what the next word will be. An easy way would be to look through a bunch of existing text and count the number of times that each word in the dictionary follows word A. The most common occurrence is probably the word you want. This isn't very good though, so let's use the previous 2 words in a sentence. Now we're looking for the probability that any word followed by any other word is followed by a third word. This complexity grows exponentially. Suppose that there were only 100 words in the dictionary, and you wanted to predict the next word in a paragraph that already contains 99 words. A pure lookup table would have 10 to the 200 values in it. This is one of those numbers that people usually explain by saying, suppose every atom in the known universe was a universe in itself, blah, blah, blah. There's no way computers can solve that problem. So we're going to need to figure something else out. One helpful trick is to use what are called word embeddings. Basically, we ask an AI to place all the words in a box so similar words are near each other. When I say similar word, I mean words that make sense in the same context. So dog and cat, a lot of words refer to both things, so they'd be near each other. This box is more than 3 dimensions, of course, and it actually encodes a surprising amount of knowledge. So the standard example people use is gendered nouns. If you put the words king, queen in the box, along with man and woman, you can actually do math. Subtract man from king, add woman, and you get queen. And yeah, there's a lot of knowledge that is embedded into these word embeddings, which is really cool. So embeddings are essentially a form of compression, but they aren't enough to teach AI to talk. A good neural network might find some other shortcuts, but in practice, there's still just too much complexity for the system to handle. We really need a way to be able to predict words in a sentence without seeing or caring about the entire sentence. Some large language models, or LLMs, will use recursion or a scratch pad to maintain memory as they read a paragraph, some way of carrying knowledge with you. The problem is, if you're only dealing with the most recent 5 words and you want to have some memory that holds on to concepts from beyond that scope, the older words will be forgotten or overwritten eventually, even if they're going to be relevant in the future. So GPT-4 uses 32,000 tokens, last I looked it up, maybe more now. And a token is like a syllable. I'm just going to call it a word for simplicity. Anyways, 32,000 words. That's how long a paragraph can be before it starts to forget things at the beginning of it. Remember, 100 words was more data than the universe could hold, so what's the magic sauce? Turns out, this thing called attention. This part was really fascinating to me. Just a quick disclaimer on this. I actually learned most of this through the hands-on tutorial, making GPT-2 in code from scratch. So I'm trying not to get anything wrong here, but this didn't come from other explainer videos, so hopefully I didn't mess it up. But I do think this is really, really interesting and definitely worth talking about, and it seems like it hasn't been talked about enough from what I've seen. But when I followed this tutorial, it felt like I was making an ant colony more than a brain. Each word had its own little notepad which contained 3 values. One was some big data that the brain uses, but the other 2 are attention mechanism values. Essentially, each word knows what it is, and it knows what it cares about. And so instead of giving this 32,000 word context to a neural network and saying, figure it out, you can use this attention mechanism to check how relevant each word is to every other word. Again, if you're curious about the math, you're using actually the dot product here between vectors. It's just kind of cool. So in an example sentence, we might be looking for a noun. Here's a paragraph without attention. Please identify the word that fits in the blank. Okay, let's apply attention. Much easier. There's still some neural network magic that has to happen, but by adjusting the context, the whole thing becomes way easier to manage. So most transformers will actually use what's called multi-channel attention, which means that each word has 8 of these little notebooks with the who I am and what I care about values. These are compared down each channel, which means that words have multiple simultaneous conversations with each other. The end result is a surprising amount of nuance in the system, just embedded knowledge in there between the words. So here's the really cool part. All these little tricks actually embed knowledge into the system. A simple image recognition network knows something about the images it's comparing. It's not smart like people are smart, but it does have some domain-specific intelligence that helps it solve this problem. When we embed words into vectors and then teach those words to recognize other words within context, and then we pass all that through a giant deep neural network, we're essentially compressing the entire internet into a single, obscenely complicated math equation with a billion variables. My favorite description of the final result actually came from Dave's Garage. He said,
ChatGPT is a little bit like an 8-year-old hyper-smart kid that has read the whole internet. So far as I can tell, ChatGPT has a great deal more knowledge than intelligence.
I completely agree with that assessment. I wanted to start my journey by understanding how these systems worked. The ultimate goal is still to determine how important AI is to my future career, to respond accordingly. Is it overhyped? Is it the future? Is it the apocalypse? Interesting note on that last one. The next video in the series is going to be about how AI is shaping our worldviews. I think a lot of people are drawing unreasonable conclusions because we aren't really stopping to think. But after that, we're going to start using AI with Godot specifically. And my goal will be to make a recommendation, both to a professional who knows what they're doing, as well as to an amateur who's just trying to learn. But I do want to end each video in this series with a call to action of sorts. For my research to this point, I believe that AI has staying power and will significantly impact some people, at least. All said, I would encourage you to take some time to move beyond the news stories and your gut reaction and really think about AI. There are a lot of important and relevant conversations happening right now. And I don't know if AI will take our jobs, replace humanity, cause the apocalypse, or fade into obscurity. But I do know that right now is the time to make your voice heard. 5 or 10 years, it will probably be too late. Legislation is being passed, inventions are being invented. In a few years, our fate will be pretty much sealed on this topic. So just understanding what people are talking about will be worthwhile, both for making informed opinions and for avoiding false narratives. Speaking of which, I did find one false narrative around AI that no one seems to be talking about right now, so I made a video on it. Here is going to be the next video in this playlist. I'll see you in that one.